In section 2.4, we were working on problems like this. We had a spring attached to a mass of, how big do you want your mass to be?
200 kilograms.
200 kilograms. All right, so in order to move this spring, a force of how many newtons? A force of 4 newtons stretches the spring. Yeah, our numbers aren't realistic, but that's okay. A force of 4 newtons stretches the spring how far? 30 miles. Let's not get quite that crazy.
200 feet?
Well, I prefer to stick with the metric system. It would make all the conversions a lot easier.
36 centimeters.
0.5 meters. All right, so, and then the spring is going to start bobbing up and down. So for our spring, what was our spring's initial position? 0, okay. That's an excellent choice. And how about our spring's initial velocity? 0. No, we can't use 0 for both, because then it would mean our spring isn't moving and y equals 0 would just be our answer. That would be too easy. But that is a very clever choice. I need a different number.
5 meters per second.
5 meters per second. Okay. So this is the typical problem that you're going to get for a quiz or for a homework. And then what am I going to ask you to do? I'm going to want you to find the equation of the motion. And then from the equation of the motion, I might also ask you, tell me the amplitude, tell me the period, tell me the frequency, all those sort of things. All right. So our formula was mx double prime plus kx equals 0. We know the mass. The mass is 200. Do we know k? No, but we can figure it out, right? We know that Hooke's law says F equals kx. So F is 4 when k is a half. Or when x is a half, I mean. So that makes k equal to 8. So we have 200 x double prime plus 8x equals 0. How do you solve that differential equation?
Wait, oh, okay.
200 was our mass.
Yeah, you gave it to him, David. Yeah, I forgot.
Big heavy mass. I'm surprised this spring can move it, but I was given. I think the spring is. I think the spring is going to break. But what's that?
200 r squared plus 8.
Okay, so what you're doing is you're writing down the characteristic polynomial. 200r squared plus 8 equals 0. So r squared is minus 8 over 200, which is the same as minus 4 over 100. And I know I could reduce further, but I really like it written as 4 over 100. How come? Because when I go to square root, I can square root top and bottom, can't I? So r is plus and minus I times 2/10. So what does that tell you about the solution to the differential equation?
It doesn't exist. Or it's an unreal number.
So what happens when we get complex numbers? Y equals, it has cosine and sine. So our solution, except we're using x, not y.
So A is 0.
So x is a cosine 2/10 t plus b sine 2/10 t. And I suppose I could have reduced that to 1/5, but chose not to. Okay, now what?
You gotta find C1 and C2.
except I called them A and B.
Oh, A, yeah, A and B.
We need to find A and B, and then we need to use that trig magic that we went over the other day to write this in terms of one trig function. But here's the good news. Somebody was very, very clever and decided that x of 0 was going to be 0. And that's extremely helpful. Because look what happens when you plug that in. You get 0 equals A, cosine of 0 is 1, and sine of 0 is 0, which means
A equals 0.
A has to be 0, which makes your life a whole lot easier. A is the number 0. So these problems are much, much easier if either your initial position is 0 or your initial velocity is 0. If your initial position is 0, A is going to cancel out. If your initial velocity is 0, B is going to cancel out.
So that means on the test, either
On the test, I would expect one or the other to be the number 0. That's what I would expect to happen on the test.
So 0 comes from the initial position.
It came from that initial condition, correct. So I still need to find the derivative and plug in this initial condition to find the B number. But then I'm going to be done because I'm going to have my solution written just in terms of one trig function. Because this one cancels out, this one's 0. All right, so I find the derivative. X prime is 2/10 B cosine of 2/10 t. And I can forget about the A cosine because A is 0, that one's 0, it's gone. Plug in this initial condition 5 equals 2/10 times B because cosine of 0 is 0, which says B is 25. So here's my answer. The path of the equation, the solution of the equation is x equals 25 sine of, I'm finally going to reduce that, write it as 1/5 t. And then I might ask you questions like, what's the amplitude? And you would tell me the amplitude is 25. And I might ask you, what's the period?
Period, isn't the period like 1/5? The period is the...
But 1/5 has something to do with the period, that's correct.
So, well,
2 pi over 1.
The period of pi, the period of sine is usually 2 pi. So this is going to be 2 pi divided by that number that's there, 2 pi divided by 1/5. So the period will be 10 pi, which means the frequency is 1 over 10 pi. And then, what was that other thing they called? Alpha, which was the phase angle, I think are the words they used. That one's easy, that one's 0.
And that's what it's offset by, right?
That's what it's offset by. This one's not offset by anything because our initial position was 0.
And the other ones, we got cosine of A plus B, and that B would have been our alpha, right?
Correct. Okay, so there's the sort of question I would expect you to be able to answer on a test.
Oh, good.
Should be pretty... It's really no different from a lot of the questions we've done in the past where you get a differential equation, you get initial conditions, you plug them in and you solve. Questions on that? Okay, the other thing that shows up in this section are some problems involving some pendulums. Oop, lost focus when I did that, didn't I? Okay, so the key to the pendulum problems is problem number 5. So we'll do problem number 5, and then we'll try one of the other ones at least. Problem number 5 says, assume that the differential equation of a simple pendulum of length L is L theta double prime plus G theta equals 0, where G equals Gm divided by R squared is the gravitational acceleration at the location of the pendulum at distance r from the center of the Earth, and m denotes the mass of the Earth. So what's that formula from G equals GM over R squared?
Isn't that like gravitation? Something?
Yeah, that's the force due to gravity, isn't it? It's the mass of the first object times the mass of the second object divided by the distance between the two objects. All right, so that's what that formula is. What's that? Still couldn't hear you.
You assume the second object is massless because it's just.
No, M is the mass of the Earth. G is the mass of the pendulum. No, that's little g. Little g is the gravitational constant. So usually the formula G is usually given as K times M1 times M2 divided by radius squared. So M2 in this case is the mass of the Earth. G in this case is K times the mass of the pendulum. Whatever that is. Turns out it's not going to matter. It's all going to go away. All right, so the first thing they do is they say, two pendulums of length L1 and L2 in locations respectively R1 and R2 from the center of the Earth have properties P1 and P2, have periods P1 and P2. Show that the ratio of the periods turns out to be that ratio involving the radii and the length of the pendulums. Okay, so we have this differential equation. L theta double prime plus G theta equals 0. Do you remember what we did for our springs on Friday? How did we get the solution to this equation? What's that? Just like we did just 2 seconds ago, right? So what we did is we wrote this actually as x double prime plus omega naught x equals 0, where what's omega naught? K over m. I'm sorry, that's omega naught squared. Omega naught is K over m square root. And so we saw that this equation had solution x equals a cosine omega naught t plus b sine omega naught t. And it turned out that the period, after we did a whole bunch of fancy trig stuff, the period turned out to be 2 pi over omega naught. How is this equation over here any different? It's got different letters. Otherwise, it's absolutely no different. Yeah, it's got an L and a theta. So our period is going to be 2 pi divided by the square root of G over L. So the period for pendulum number 1 is 2 pi divided by the square root of, now remember what little g was. Little g was big G times big M divided by radius squared. So that's going to be big G, big M divided by radius 1 squared. And then we still have the length on bottom, so that's length 1. I'm going to rewrite this. This is 2 pi times R1 square root of L1 divided by square root of GM. So what did I do to rewrite that?
Well, you took square root of top and bottom separately, and then you have the bottom took the since they're multiplied together, you took the r squared out.
I took square root of top and bottom, The square root of r squared is r, and then I flip my fraction, didn't I? All right. By the exact same reasoning, what's P2 going to be? Same thing, except it's going to have R2 and L2. So we have 2 pi times R2 square root of L2 divided by square root of GM. All right, so here's the answer to problem number 5. If I now take this P1 and divide it by this P2, what's going to happen?
The square roots of GM are going to cancel.
The square roots of GM are going to cancel, and the 2 pi's are going to cancel. I'm left with P1 over P2 equals R1 square root of L1 over R2 square root of L2, which is exactly what the problem said they were supposed to be. All right, so you're going to use that result to answer problems 6, 7, and 8. Except I'm going to do problem 6 for you. Problem 6 says, a certain pendulum keeps perfect time in Paris, where the radius of the Earth is 3,956 miles. But this clock loses 2 minutes and 40 seconds per day at a location on the equator. Use the results of problem 5 to find the amount of equatorial bulge of the Earth. What do they mean by equatorial bulge of the Earth?
Like, is it like, how far does it bulge out?
Yeah, the Earth isn't a perfect sphere. At the equator, it's actually bulged out wider. The radius at the equator is actually more than radius at other points off the equator. There's actually a bulge there. Okay, so what do we know? For number 6, we know in Paris, I'll call this one R1, I guess, the radius it told me was 3,956 miles. And I'm trying to find R2, the radius at the equator. What do I know about the length of the pendulum? It's the same. How come? It's the same clock, right? The clock has just moved from Paris to the equator. So we know that L1 equals L2. So we don't really need to worry about that at all, do we? Those are just going to divide out to be 1. All right, the last thing we know is that this clock keeps perfect time in Paris, but loses 2 minutes and 40 seconds a day at the equator. So I need to know the respective periods. So what's the period of the clock in Paris?
Perfect, so it would be 2 pi.
And then how does that relate to the period of the clock on the equator? Not quite the same. Because on the equator it loses time. So its period must be different. It's not swinging quite as fast, is it?
Would it be 2 pi minus the time that they said that?
Not quite. Alright, so it gives us that the time it loses 2 minutes and 40 seconds per day. Alright, so my question is, how many seconds are there in a day?
3,600.
How much? How many?
Is it 3,600?
That's minutes in a day.
Times 60.
How many? There are 86,400 seconds in a day. So what's the period of the first clock? Well, what's the period of the clock in Paris? The reality is I don't know. But it needs to make 86,400 swings, and then its period would be divided by some number n, where n is how long it takes it to make a swing. And I don't know how long it takes it to make a swing. Turns out it's not going to matter if you simply use the number 86,400. You're going to get the right answer. All right, so it takes 86,400 seconds for 1 day for this clock in Paris. What happens when the clock goes to the equator? It takes slightly longer. So it takes 86,400 plus an additional 2 minutes and 40 seconds. So how long is 2 minutes? 2 minutes and 40 seconds. So how long is 2 minutes and 40 seconds? 160 seconds. So that's going to be 560 divided by, again, I don't know how long it takes it to make a swing. Turns out it really isn't going to matter. Because we can now set up our ratio. We're going to have 86,400 over n divided by 86,560 over n. How come that divide by n doesn't matter? They drop out. Equals square root. No, r doesn't have square root on it, L does. R is just 3956 divided by R2. And we just solve for R2. So we cross multiply. We're going to have R2 is 3956 times 86,560 divided by 86,400. Punch some buttons on your calculator and you tell me the answer is? What was it?
7.33.
7.33 miles. We were dealing in miles. So how far does the Earth bulge at the equator? About 7 miles. In some places, yeah, roughly 7 miles. Yeah, it's not nice and smooth. That's true. Questions on that? All right, so problems 7 and 8 are kind of similar. I'll let you give those a try. The last thing we have in this section is what happens if we have damped motion. For damped motion, our equation changes slightly. We have mx double prime plus cx prime plus kx equals 0. So it's damped, but we're still unforced. How do you solve that equation? Same way you've been solving all of them. So mr double prime, or mr squared, I mean, plus cr plus k equals 0. And then how would you solve? How would you find r? Calculator? Or algebra? The answer I'm looking for is use the quadratic formula. That's the answer I'm looking for.
That's on a calculator.
R equals, yeah, but I got letters here. I don't have numbers. R equals negative b plus or minus the square root of b squared minus 4ac. That's kind of confusing because b is the letter c and c is the letter k.
Yeah, I was confused with
That's a little confusing.
B to writing C.
So B and a C, because B is C in this case, and C is K. So does that mean B is K? No. Divided by 2A. So there's the answer you would get. That's the quadratic formula. That's all I did. Except it's confusing because I was saying the letter B but writing the letter C. And when I said the letter C in the quadratic formula, I wrote the letter K. So that's a little funky, but it works out.
Is it gold and white or is it black?
black and blue, by the way, but that's a whole
Yeah,
other
it is
story.
black and blue.
All right, so now, what can happen?
Imaginary numbers?
You might get imaginary numbers. When would you get imaginary numbers?
If there was a negative underneath the square root.
Yeah,
So-
if 4AC is larger
If- If c squared minus 4mk is less than 0, then your answer is going to look like y equals a, no, that's not what I want, e to the at times a cosine omega naught t plus b sine omega naught t. And this possibility is called underdamped. So it's possible that the thing underneath the square root is a negative number, which means you're going to get complex answers, which means you're going to have an e to the a, and then you're going to have your...
George, can you slide that over just the other way?
Yep. No, this is called underdamped. So this is what we saw when I bounced the spring the other day. We saw the trig wave, right? But what was happening? It was getting lower, and that's what this exponential thing does. This a value is going to turn out to be a negative number. And so when t gets bigger and bigger, what's going to happen to this e to the at thing? It's going to get smaller. So that's what's going to cause your amplitude to decay. So this is what we saw with my spring that I bounced up and down the other day. That was an underdamped situation. You get the cycles, but the cycles are decaying. What else could happen? It could be overdamped. What would overdamped mean? It will move.
It'll exponentially grow the amplitude.
No. No, that's called resonance.
Yeah.
This thing under the square root, that's called the discriminant. The discriminant could be negative. Could the discriminant turn out to be positive? Yeah. Okay. If c squared minus 4mk is positive, then what kind of answers are you going to get?
Real.
You're going to get two real answers, aren't you? So if you get two real answers, what does your equation look like? Y equals c1 e to the r1t plus c2 e to the r2t. And it will turn out that both of those r numbers will be negative values. So what does that tell you? It goes to 0 really fast. So this is called overdamped. You don't even get one complete cycle. It stops almost immediately. Your damping is so big that it stops almost immediately. Thanks. The absorbers in a car would be a good example of something that's overdamped. Yeah, you want the bouncing in your car to stop almost immediately. And so I think that would be a good example of something that's overdamped. The spring, the shock absorber is bigger than you need to stop the spring, but you want that. You want it to stop quickly. The third possibility c squared minus 4mk could actually turn out to be the number 0.
And
What happens, what's the equation look like if c squared minus 4mk happens to be the number 0? No, you only get sine and cosine when you have complex answers.
it's just constant. C1 plus C2 is just 0.
How many answers am I going to get here? I'm going to get one answer, but I need two. We have a repeated root. That's exactly right. So your answer will be y equals c1 e to the rt plus c2 t e to the rt. You will get one repeated root. And this situation is called critically damped.
Would it be C2 T to the RT or would it be RE?
Yes, but our variable here is t, not x. Yeah, we multiply by t. That's an excellent question. I don't know. Well, no, it moves, but again, what's going to happen when t gets big? These are both going to go to 0. So again, it's going to stop pretty quickly. So it's possible that the shock absorbers in your car might actually be a critically damped situation. I'm not sure.
It would be like, instead of having the shock absorber, you just have a steel rod. It doesn't That might flex a little.
Well, that would be over damped would be the steel rod. It stops it almost immediately. The critically damped, it stops it pretty fast, but you get a little bit of play in it.
Okay. That's too much wear and tear on the components.
Correct.
So like,
Yeah.
consider the shock for certain materials.
How do you get resonance?
How do you get resonance? To get resonance, you have to have an outside force.
Okay.
Could run over bumps that are like evenly spaced for a long time.
Right. So to get resonance, you have to have an outside force, which means you have a non-homogeneous equation, and we're not very good yet at solving non-homogeneous equations.
So these,
Until you come back Wednesday. Wednesday we will start learning how to solve non-homogeneous equations. And so then by the end of the week we'll come back to springs and we'll talk about what happens if you have a force out here. And you can get something called resonance happening then. And we'll talk about resonance. Okay, so your homework problems are going to look like this. You might be given m equals 3, c equals 30, k equals 63, x at 0 is 2, and v at 0 is also 2. And the directions are basically solve that situation, determine if it's underdamped, overdamped, or critically damped. Write the equation. 3x double prime plus 30x prime plus 63x equals 0. How would you solve that differential equation? I'm going to go ahead and divide everything by 3 as long as I'm writing that down. Everything divides evenly, so I'm going to divide by 3. But you're right, I would write my characteristic polynomial r squared plus 10r plus 21 equals 0. I grabbed my calculator and I used the quadratic formula. It tells me? Oh, it happens to factor, doesn't it? Oh, yeah. It's r plus 7. I wasn't even thinking.
I was like, you're gonna
Trying to kill a mouse with an elephant.
Trying to kill a mouse with an elephant gun. Yes, I was. R equals negative 7. R equals 3. Negative 3. So what's that tell you? Underdamped, overdamped, critically damped?
overdamp.
Overdamped. When you get two real answers, that's overdamped. And those R's will always turn out to be negative in this case. Why will the R's always turn out to be negative?
It gets closer to 0.
Well, it does get close to 0, that's true. But why from this equation are you always guaranteed that the two R's will be negative? Because you're always going to have a plus here because C is always a positive number and K is always a positive number. So this is always going to factor as R plus and R plus. So it's not going to be negative. All right, so our solution is x equals C1 e to the negative 7t plus C2 e to the negative 3t. Really not much new there.
What about the x naught and the y naught?
Well, I gotta plug those in still. I'm not done
I thought
yet.
you said we're done.
I didn't say we're done yet. We're getting close. Plug in our initial conditions. We have 2 equals C1 plus C2. And then velocity, of course, is the derivative. So I take the derivative. X prime is negative 7C1 e to the negative 7t. minus 3c2 e to the negative 3t. Plug in the second initial condition. I get 2 equals negative 7c1 minus 3c2.
Or you could just do the matrix, right?
I could at this point do a matrix.
Multiply the top by 3. And just
I think it's almost easier to do it by hand, but absolutely I could use a matrix. I'm going to do it by hand because my calculator is way over there and I don't want to walk over there and get it. I would multiply this top one by 3. 6 equals 3c1 plus 3c2. 2 equals negative 7c1 minus 3c2. Add them up. I have 8 equals negative 4c2. C2 is negative 2.
wait, wouldn't it be negative 4c1?
Oh, yes, C1. I'm sorry. Got going too fast there. So C1 is negative 2.
Just plug back into the original.
Plug it into there. C2 is 4.
Yep.
Yes, if you want to use a matrix there, you can. I think it takes longer. That's my opinion. X equals negative 2 e to the negative 7t plus 4 e to the negative 3t. Questions on that? Max?
How did you get 2 equals c1 plus c2?
I took this initial condition
Oh, geez, okay.
and plugged it in.
Okay,
E to the 0 is 1, so it's very nice that they picked the zeros for me. Makes all the e's go away. Very thoughtful. Almost as if they planned that. Yeah. Other questions?
So the result when you answer the x equals 3, 2, and so on, what is that actually, is that graphically just saying how far you traveled in the airplane? Or what's that telling us?
That's an excellent question.
yeah.
Can I borrow your calculator, please? Guess I didn't bring mine at all today. So you see what's happening. We started at a distance of 2. Our initial velocity was also 2. So it started going away. So you see a very small increase right there. But then as t gets bigger, these e's get close to 0 very quickly. So it started moving away. It turned around and came back. And it came down, and you can see by the time this is, that's probably 2 seconds right there would be my guess. Nope. So there's x equals 2. By x equals 2, within 2 seconds you can see the thing is almost back at rest, and it's not, its velocity is practically 0 also.
I got back to less than 1.3.
Yeah. So it moves slightly, but it doesn't even make one complete cycle up and down like we saw with my spring bouncing the other day. It goes up just slightly, comes back, and it stops almost immediately. It's practically stopped within 2 seconds. Back
You
to
said
it.
that was overdamped?
That's overdamped.
Now, had it been critically damped, would it make one complete oscillation?
If it's overdamped, if it's critically damped, it will cross the axis once, and then come back up and stop. But I mean, it may just barely cross the axis. It might be hard to see it on the calculator actually, but it will cross once.
And so then the x is just a position from wherever you're starting from the rest position, right?
Other questions? Thank you, Jonathan. All right, so that's pretty much all there is in this section. I mean, there's more problems that have the same sort of thing, but there's nothing new. You're going to write down your characteristic polynomial and solve.
So we done for today?
We are done for today.